Okay, question 7 says a thin metal plate is in the shape of the portion of the plane 2x plus y plus z is equal to 8 that lies in the first octant. The mass density delta, which is measured in kilograms per square meter, at the point xyz on the plate is proportional to the distance from the point to the plane z is equal to 16. Find the mass of this plate. All right, so here is picture of the plate, right? So we have this plane 2x plus y plus z is equal to 8, and we're just considering the portion of that plane in the first octant. All right, and the fact that the mass density delta at a point xyz is proportional to the distance from the point to the plane, z is equal to 16, we can say that delta then is just 16 minus z, right? Because if I choose any point on this blue plate here, the fact that the z coordinate, right, it's going to be less than or equal to 8, the plane z equals 16 is up here. So I just want the difference between the height of 16 on the plane and the altitude of our point, which is just the point's z coordinate. So 16 minus z, and then we have this constant of proportionality, k there. All right, and so the mass then, that's just going to be the surface integral of this mass density function delta. And so now let's go ahead and parameterize the surface. And here it's easy to solve for z. So z is just 8 minus 2x minus y. And so I'm just going to use an explicit parameterization. So r of xy here is just x comma y comma 8 minus 2x minus y. And now here also note that the domain, right? In other words, the region in which we're letting this point xy range through is the projection of our surface onto the xy plane, and that's going to be this triangle here. Okay, so when we go to set up the integral, we are going to have to integrate over this triangle, and so we'll have to find the equation of this line and be careful with the bounds and all that, right? Up to this point, we've only seen integrals over rectangles in the UV plane, which is, of course, ideal, but this is not bad. Okay, so now what can we say? Well, how about the differential surface area element ds? Well, since we're using an explicit parameterization, okay, we're going to compute the square root of 1 plus the x derivative of g. Now g here is just this expression right here, right? Z is equal to g of xy, which is just 8 minus 2x minus y there. So take the x derivative of g and square it, and then the y derivative of g and square it. Add that to 1, take the square root, and tack on the dA. That is going to give us this differential surface area element. Okay, now gx, that's just negative 2, and gy is negative 1. So this simplifies to simply square root of 6 dA. Okay, that's pretty nice. And then if I want to evaluate my mass density along the plane, okay, given that delta is just 16 minus zk, I'm just going to replace z with this expression g of xy. So I'm going to get 16 minus the quantity 8 minus 2x minus y. There's the constant of proportionality k there. And then this simplifies to 8 plus 2xy plus y, all multiplied by k. All right, so now let's go ahead and substitute in all the relevant pieces here. So we have delta there evaluated along the plane. That's this quantity in green, and I just pushed the proportionality constant k out in front. ds, that's the root 6 times dA, and we're going to integrate now over this triangle in the xy plane, right? R here. All right, so to do that, I'll go ahead and fill out that triangle with vertical strips. So y will vary from 0 up to 8 minus 2x. That's the equation there for that blue line. And so those are the bounds on y, and then x is just varying from 0 to 4, right? As we stack these vertical strips from 0 to 4, we'll fill out that triangle. And this is a bit of a messy integral, but it's not the worst thing. And when you crank through it, you wind up getting 640 times the square root of 2/3, and then there's that proportionality constant k. And the units there would be kilograms because the mass density there was given in kilograms per square meter. All right, well, that will do it. Thanks so much.